Okay. Hey everybody, I'm gonna get started. So as an overview of what I did last week, I wrote this small little WebGL sketch from scratch. It's just this one HTML file that creates a WebGL canvas, and sorry, getting chat set up. Okay. Sets up a canvas, and then I have a radial grid mesh centered at the camera that I'm displacing with some sine waves for the height field as just kind of a first attempt at what eventually I want to be an ocean. So right now there is just a single point light at the position of the camera, and so it's just moving around with me as I move around, and then the surface is just purely Lambertian diffuse shading. So this week what I want to do is I want to set up, I'm going to try using the Cook Torrance microfacet shading model with a GGX BRDF so that I can get a specular reflective ocean surface. So I have a couple of papers and tutorials open. I think I'm going to be largely working from the Learn OpenGL tutorial because they have some concrete GLSL to work from, and I haven't actually implemented this before, so alright, gotta go calm my dog down. One sec.
Good boy.
Sorry, Hubble was getting upset, so I needed to calm him down. Okay, so yeah, I have some reference open to work from for implementing Cook Torrance. He's still barking.
It's okay, bud. Thank you, bud.
Okay, hopefully he'll be calm now. Okay, so I think the first thing I'm gonna do, so I've saved this. I've made a commit so I don't lose where I was at the end of last week. To start with, I'm going to, I think for now I'm going to turn off my fog, my atmospheric perspective, so that I can see everything more clearly. And then I'm going to just replace my point light with a directional sunlight. So this was my atmospheric perspective. So now you can see all the way to the distance clearly. And then here's my light. So I'm still going to just use a purely white light, but I'm going to make it a directional light. So instead of dotting the normal with the view vector, I need to be dotting the normal with just, so if the normal is this, and the sun is coming downward, then I need to dot it with the upward vector. So for now, I'll just make that be, I'll say negative sun, and then my sun vector will be will be y up. Let me see if that works. I might have it backwards. I think I'm doing something wrong. So I have my normal, which is computed from the height field. And then I have my sun vector, which I guess it depends on my projection matrix, whether y up is positive or negative. But yeah. The thing that's confusing to me is the fact that it seems to be dark in the distance and bright up close, but I'm not... Oh, because I still have a inverse square fall off, which makes sense for the point line, but not for the sun. Okay, now it's just ultra bright, so... There we go. So yeah, that's a downward diffuse light. Let me turn it a little bit higher. Okay. I'm gonna rotate it just a little bit. A normalized vector, which is pointing downward. Oh yeah, that makes sense. That negative y is downward. That's what I thought in the first place. With a little tilt in the x direction. Maybe make it a bigger tilt and let's see what happens. SPF 50. Yeah. Dangerous sunlight levels. I'm curious what is leading to that kind of rippling when I do this. Like there's some kind of grid-shaped weird aliasing pattern thing that's happening when I move around quickly. And I'm not sure what that is. It might honestly be the tessellation. I'll figure it out later. Anyway, I think I'm gonna add quick up and down keyboard controls so that I can see from up and down. So that I can see from like a higher vantage point. And maybe I should add camera rotation too, but so okay, let me do let's just do R and F for my up and down. And I should have a more systematic way of handling key events, but I'll have that later. Okay, let me look up key codes for R and F again. $82 and $70. So okay. So now I have my R and F, and then what I should do is add R, F, and then I'll add a Z coordinate to my offset. And then when I feed in offset as a uniform, I also need my Z. So uniform 3 of V, and then finally my shader where I take it in needs to be a vec 3. And then I just add my Z to the output of my height field. Hey Loney, thanks for tuning in. Okay, so let me see that. Yeah, there we go. Oh, they're both making it move downward. So it needs to be. Oh, and also I'm swallowing these key events. I'm just going to get rid of all of this. And now I'm not swallowing the key events anymore. Yeah, so this lets me see from different angles, which is nice. And yeah, I think I'm confident now that that issue is just a too low level of tessellation. Because it's just, you can see the vertex interpolation. And since I'm computing normals per vertex, yeah, that's right. So let me try just upping the tessellation level, see what it looks like. Where was my spacing? R equals ring over rings to the fourth. Make it squared maybe. And then maybe let me just add more rings here. Why did it get cut off? Oh yeah, that makes sense. Okay. Just add more triangles. Okay, I think there might be something I'm doing incorrectly and not just too low of tessellation. Like maybe my normals aren't good. Not sure. This might be fine though. Go back to fourth power. So I'm increasing the spacing by too much. Oh, maybe I need to do this. Maybe I'll just leave it for now. It looks fine up close anyway. Maybe if I computed the normal in the fragment shader, it would look better. Maybe my far plane is too close or something. It's hard to debug this without something like RenderDoc. Okay, let me revisit my normal computation. Yeah, maybe these are being computed with too low of precision. That seems likely to me, I think. Yeah, that looks much better. I think that's what the problem was. Okay, That looks like it's supposed to. Roughly, at least. Yeah, and then let me see if I can get my far plane further out. So I'm not sure if it's getting clipped or if that's just the limits of the mesh. Okay, I think it's the limits of the mesh. Yeah, I push it out really far and it doesn't change anything. There we go. Yeah. I guess it gets pretty obvious that we're scrolling the height map rather than the mesh itself because of the... Hey, Sinto. What's up? I'm trying to get my mesh spacing right so that this doesn't happen when I move around. But maybe that's just an issue with using my constant tessellation radial grid. Maybe that's just unavoidable. And the better way to do it would be like some kind of just Mikuing. You working on the corral? That's like such a cool idea to do. I'm like jealous of the idea. Okay, now it pretty much goes out to the horizon. Not quite. Oh yeah, that's very low resolution. It's very janky. Oh, here's the thing. Yeah, if I change my mesh, then I need to change my finite differences calculation also, I think. Maybe. Okay, anyway, I'm gonna try not to spend too long on this because I want to move on to the shader. Yeah. Okay, I think this is a good spot to leave it in. I'll deal with the problems that are happening later. At least from this up close, it looks pretty nice. Possible that I'm running out of triangle indices. Let me just rule that out as a possibility by switching to 32-bit. Yeah, that was the problem. Okay. I just have a massive amount of triangles. Now, I have more than 65,000 because the indices don't fit in a 16-bit int. I'm going to tweak the finite differences one more time. Oh, I'm made a typo. Okay, yeah, we're aliasing a lot in the distance, but the normals are okay now. Okay. Yeah, I'm not quite sure what to do to prevent that. It looks kind of nasty. I think I'm not decreasing the resolution enough as it goes out into the distance. I think maybe that's a problem with sampling the height field, and I should like band limit the height field, smooth the normals more. Anyway. At least it doesn't look broken, it's just extremely aliased. Okay. So now I can move on to the ocean shader part. So, right now I'm calculating my lighting as a dot product with the sun vector, and that's about it, which is just kind of a purely diffuse reflecting surface. And what I want to change it to is a specular surface. So I want to use the Cook-Torrance microfacet model, which kind of has, I may not be like referring to the exact scope of it correctly, but the way I understand it is it has kind of three aspects to it. It's got, so basically it models a surface, like right now, this is kind of an ideally perfectly rough surface in a way, like it's taking in, every point is taking in a hemisphere of light and then perfectly evenly scattering that light back out among the hemisphere. So for a given ray that is striking a point on the surface, it's perfectly choosing a random uniform direction on that hemisphere to go back out. Although it's not accounting for any secondary ray bounces here, it's just primary ray shading, so and there's not even shadows, so it's lacking in a lot of realism or subtlety, but that's the model that it's currently using. So what I want to change it to is, rather than having a perfectly random distribution of rays, I want to have analytic sine wave band limit. Interesting. Let me check this out. Oh yeah, I did see this back when he posted it. It might be possible to do this to the Gerstner waves when I implement those, but it seems kind of difficult to figure out. And it honestly might be better to do the ocean height field in a texture rather than in an analytic like wave simulation, but I'll figure that out later. That's like an extra step of work to do. Okay, so back to what I was saying about lighting. So the microfacet model is that rather than having a perfectly smooth surface which acts like a mirror, where a point light shows up as like a infinitely small point reflection on the surface, and then rather than a perfectly rough surface where you where it looks like this, somewhere in between you model it as some probability distribution of facets like this, And so there are two aspects of the facets. There's the normal distribution function. Where'd that go? And the geometry function. So the normal distribution function is it approximates the amount that the microfacets are aligned with the overall normal of the surface. So if you model the surface as like a little patch here, this is the normal, and then the microfacets, the normal distribution function is an approximation for how aligned on a micro level the surface is with this normal, and then the geometry function is a model of if the microfacets are shadowing other microfacets, how much to dim the reflected light from that. So, and then the third thing is I don't fully understand whether you can derive the Fresnel effect from the microfacet thing or not. I don't think so, but that's kind of the third important part here, which Fresnel is basically where as the reflection angle becomes more grazing, there's less absorption or transmission and more reflection. And that ends up showing up in practice as kind of the rim around something gets more reflective. You can see that in Wikipedia has like a photo of, yeah, so like for these photos you can see the grazing angles have more reflection occurring. So obviously since I'm rendering an ocean, that's going to be important. So so to start with, I'm going to try to get just the normal distribution function aspect of it. So I guess, yeah, so GGX, I guess, is purely referring to the normal distribution function. There are a couple of others that are available to use. Let me find, yeah, so this paper talks about, there's this one introduced the GGX distribution, which is in contrast to the previous existing ones called Beckman and Fung. And so those are like the simple baby versions, and GGX is like a bit more expensive, but looks a lot nicer. So let me just try implementing the normal distribution function of GGX. So here's my where I'm dotting with the sun. So here's my light vector. I'm going to comment out the current light calculation, and I need to. Yeah, it is kind of a terrible name because it's the name of another type of distribution. Yeah, so I feel like it's not too confusing in context, but yeah. So GGX has a parameter for roughness, and then it takes in, just like we have here, this is our n.v. Let me, yeah, they're clamping their n.v at 0 also, so that makes sense. So let me have, instead of calling this light, I'm going to call this n.v. Hey, Lewis. Well, yeah, you can say Gaussian, but I feel like it's probably less common that if you're talking about Gaussians, nobody is going to get confused that you're talking about microfacet reflection models. Probably. It's possible. Anyway, so I've got my n.v value, and then let me just say roughness is 1. So the GGX distribution in the paper looks like this. But I think, I'm not 100% sure if this is like the usable formula to use in a fragment shader. So I'm just going to go by copying from from this tutorial for now. I did some reading beforehand, but I need to more fully understand how this is used in a non-path tracing context where you're just purely sampling the BRDF, which is I think what the original paper presents it as. So let me just copy paste this in and get it in a form where I can use it. So we have roughness squared, and then we have that thing squared again. So roughness to the 4th. Is that in the original? Curious. Yeah. There's something to the 4th. Let me see if they have GGX equation here. So alpha is roughness squared, and then you square alpha again. That makes sense. And then you have n dot h. So, okay, so what h is, this clicked for me earlier today. So if we have a patch here that we're shading, and then this is the normal, and this is the light over here. So this is our light vector, and this is our normal vector. And then this is our view vector. The half vector is, okay, this diagram kind of sucks, but the half vector is halfway, it's like the bisector of the view vector and the light vector. And the reason that makes sense is if you have light shining in a ray from the light to the surface, the time it will be perfectly reflected in like a mirror is if the half vector is exactly aligned with the normal vector. So let me draw another one of these that matches that. So here is our patch. Here's I. And then here is the light. So if we have light vector hitting the patch, and the normal is exactly the bisector of the light vector and the view vector, then the perfect reflection takes it straight to the eye. So that's why the half vector is important, because you're basically comparing the position of the half vector to the normal, and that gives you how much of the incoming light is reflected towards the eye. So I need to calculate H, which I think they did earlier in here. And if I have, let me just call this L for my light vector. Not using, and then let me call view V now. So now I have and let me just call normal and just so it looks like the equations. So our normal is already normalized at this point. Our view vector, let's just normalize it here just to reduce the possibility of making mistakes. I'm sure it is, like, I think that that's true in terms of the actual shape of the equations, and the way that I'm thinking about it, I think is relevant. Like it's like it is true that a perfect mirror reflection happens when the normal vector is the half vector. And so I think that's why it is able to simplify the equations or reduce the redundancy in specifying it. But yeah, I'm not sure. So we have N, we have V, we have L. Oh yeah, we can't normalize this because our atmospheric perspective depends on, we can do this. Depends on the length of the view vector. Okay, so but yeah, this is like somewhat new territory for me. I've written path tracing stuff before, but I need to solidify my knowledge of the specifics of all this stuff a lot more. Okay, so H is halfway between the view vector and the light vector. So that's just, if they're normalized, you can say N plus, no, sorry, it's V plus L. Yeah, there we go. So here's our half vector. So I'm a little confused what the difference between these three functions is. Anyway, so the GGX distribution, we have roughness squared, we have n dot h, this will work now. We're clamping it at 0, n dot h squared, and then the numerator is a squared, like if you look back at this equation, where did it go? A squared. And then on the bottom you have pi times this whole thing squared, denom. And denom is n dot h squared times a squared minus 1 plus 1. Okay, I'm going to compare that. Yeah, and this, I remember chi is just the binary function for whether the m dot n is greater than 0, I think. So we can just ignore this for now. This is like the clamp thing. And then I'm not sure why there's a cosine and tangent here, but there's not in here. But maybe they're just using dot products here, and cosine and tangent are a way of expressing the same thing. Anyway, I'm gonna implement it and then see how it looks. So here's my GGX thing. Instead of return, I'm gonna say, so here's my NDF, output of the GGX. And I'm just gonna take that as my light for now and see what it looks like. Okay. Then we have an error. Yeah, okay. Pi undeclared. Yeah, I guess they declare pi in their shader. So that's the n.h term. n.h squared term. Yeah, we are getting very speckly aliasing in the far distance. So I'll need to deal with that. at some point. I'm just a little confused why it'd be giving me this like constant value. Which I think means oh, because roughness is 1, yeah. So let me change roughness to 0.5 and see what we get. And then as we bring roughness down to 0, okay, I'll assume that that's correct for now. This is just the GGX term. So they calculate the NDF, which we're doing, and then they calculate the G, which is the Smith geometry function, which, like I was saying earlier, is kind of the amount of self-shadowing due to the roughness due to the microfacet shapes. Okay. So let me do the Smith part now. So that takes n dot v and roughness. So R is roughness plus 1.0. Oh, what's the paper? So I have a couple of them. I have the original Cook-Torrance microfacet model paper, which doesn't have GGX in it. It just uses the, I think, Fung and what's it called? Beckman in it. So you see it has these lobes for the Beckman distribution. So this basically introduced the microfacet model, and this is the kind of thing it looks like. And then this one, the paper is nominally about refraction, but in practice, what it introduced was the GGX distribution, and that's used for just reflective stuff quite a bit. So that's what I have the paper open for, even though it's nominally for refraction. The pictures at the end look pretty cool for the roughness and the refraction. Okay, so I've calculated GGX. Now I need to calculate the Smith, which ends up calling the Schlick thing for both n.v and n.l. I don't really understand. Okay, I'm just gonna copy paste for now, and then I will off stream actually understand this stuff, and maybe come back on a later stream and explain how it works. But I just want to get it working today. Yeah, it's cool. It does like the distance dependent blur that you get. Like you can see how the farther away circles are more blurred than the close by ones, which is what makes sense for a rough refractive surface. which I think for real time, the way people usually do it is you have the translucency pass, and then you generate MIPS of your opaque frame buffer, and then you can sample blurred different levels of the MIP blurs when you're depending on the Z value in the frame buffer at a particular point. So that's how you would like approximate this effect in real time, I think. Anyway, so yeah, I'm just copy pasting in these functions. May as well just copy this one in too for cleanliness. Let me see if it still compiles. Oh yeah, yeah. Okay, so we have just the GGX term working now. So let me add in the Smith thing. I have all of these values, so I'm good. And then the Cook Torrance BRDF depends on the normal distribution function, the geometry function, and the Fresnel term. I'm not sure where they calculated that. Oh yeah, so they also have the Schlick approximation to Fresnel in there. So let me add that in, which is basically just you have the angle, and it's just like they have to the 5th power of 1 minus cosine. It's just like a polynomial approximation. Cauchy distribution? Do you mean the Fresnel-Schlick approximation is Cauchy, or something else? Anyway, let me plug in. Yeah, so I think for F naught, it's just kind of a per material thing. So since I'm doing water, I'm going to say F naught is 0.02. So when I call my Fresnel-Schlick with cosine of theta, which is h dot v, yeah, that makes sense. Fresnel-Schlick feed in this. GGX is Cauchy? Okay, yeah, I'll have to read more about that. I'll remind myself what Cauchy distribution even is. Okay. Okay, so Fresnel-Schlick, and then we're feeding it 0.015, was it? Or was it just 0.15? No, it's 0.02, I remember it wrong. So that's our F naught for water, which is just like a permaterial value of the response at a 0-degree angle looking directly on. So now we have F, NDF, and G, the Fresnel term, the normal distribution term, and the geometry term, which are kind of the 3 essential parts of the Cook-Torrance model. So now let's calculate Cook-Torrance. So we just multiply all these together, and then the denominator is, I think, where was the full Cook torrents? Yeah, it's this. It's the 4 times the angle out dot normal and angle in dot normal, n dot v and n dot l. Oh, wrong place. So that's our denominator, and then the specular term. Okay, so they just clamp denominator at 0.001 to prevent nans and infinities. Okay, so oh wait, so one of these f must be a vector. Oh, because it's a color. It's per color. So you do it per color in the case of metals. In the case of dielectrics, the F naught is white for all of these materials, which means, oh yeah, it should be, wait, am I in linear or sRGB? I'm in linear at this point, so I should be doing 0.02. Yeah, anyway, and what this means is dielectrics reflect white, so as you go to glancing angles, all the color is white, whereas for metals, they start out much more highly reflective even at direct incident rays, and the color is not white. It's like a per metal color. So specular is, they just divide numerator by denominator, and then clamp it at some epsilon so that you don't get infinities. And then let me add back in my, well, let me do purely specular first. So I probably shouldn't be multiplying by the color here, but I will anyway, and let's see what it looks like. Cannot convert from, oh yeah, because I gotta do a vec3 here for my color value at F naught. Yep. Not sure what line that's on because I don't have my shaders in a separate file. Line 75 cannot convert from 3 component. Oh yeah, I think I need it. Yeah, vec3. F is a vec3. Take the specular color. I think the denominator is a float, right? Yep. That's what I had wrong. Yeah, that's what I was a little bit confused about too. And I think that was what I wasn't sure about with the GGX equation here, whether that was like BRDF, and then this is calculating like expected value for basically. But I think that if you're not talking about diffuse, no, yeah, it's not just a single ray. If you're doing like roughness and smeared like specular stuff like this, you're not just sampling one ray. You're basically like approximating the integral over this whole lobe, I think. And so yeah, I'm not 100% sure how that connects this distribution to these approximations. But yeah, I will hopefully understand this better eventually, and I can maybe explain it on a later stream. Okay, Yeah, specular is a color. So yeah, let me just comment these out and say that color equals specular. And it's just going to be ranging from white to black for now. There we go. Let me try making roughness be 0. And then let me try making my sun vector be perfectly up. Yeah, so I think I'm doing something wrong for it to be this dark. Do not think I'm doing this right. I don't think so, because they're varying roughness from 0 to 1. Yeah, I don't see where it would be doing that. Interesting. I've heard of the Disney BRDF, but I don't really know what it is compared to. Is it combo of Lambert and GGX or something like that? I'm just gonna look this up real quick because I'm curious. All right, no simple explanation on there. Parameterized, okay, that makes sense. Yeah. So this is not what I want, because it's black everywhere. So let me try setting it to particular terms. So like, let me try setting it to just the Fresnel term. I think it should be getting more white than it is. H is normalized V plus L. L is normalized. V is normalized. I assume so, yeah. I assume that's what Blender's thing is. Okay, cool, that makes sense. Yeah, when I was trying out LuxCore in Blender, they call their like default one the Disney BRDF instead of what Cycles calls principled BSDF. But yeah, I think it's similar. There might be more things in the list for blenders. But yeah. So I'm pretty sure my F should be varying more than it is. I'll go through the So Fresnel Schlick returns F0 plus 1 minus F0 times. So it's basically lerping between F0 and 1 minus F0. And I'm feeding it n.h as cosine theta. H.v, sorry. Which seems right to me. H.v clamped at 0, F0. Like, this seems like it should be Separate specular. That's interesting. Yeah. So like less hardcore PBR basically for more artistic control. That's interesting. So let me try looking at each of these terms individually. So if I look at the Smith G term, it's just black. If I look at the NDF term, oh yeah, I should remember to vary the roughness because that's the whole point of this. Let me keep it at 0.5 just so I can... I don't think that G should be black. These are just like not varying very much. The NDF is giving me these like massive aliased speckles in the distance, but it's not giving me like any normal specular behavior, which is confusing. Yeah, it's interesting. I kind of feel like after you're familiar with how the PBR stuff works, then you can depart from it again, having like learned from it, and you're better off for it, even though. But yeah, I think it's overrated to have like perfectly reference like ultra realistic renderer for artistic purposes. I was thinking about this, how a lot of the kind of like Cinema 4D like tape look type of like Tron like neon Instagram type of art these days, everybody's putting it through so much like color grading and volumetrics and stuff that makes it look more like a sci-fi illustration, which makes it so that the quality of the ambient occlusion and global illumination like doesn't matter as much in terms of how accurate it is or unbiased it is, because it looks more like just a pure artistic impression of that anyway, which I think means you could get away with more real-time style global illumination techniques and it would look just as good. That makes perfect sense though, yeah, for the G buffer. Yeah. Alright, so I'm a little confused why I'm just getting this like flat, non-varying values. When I have n.l is the diffuse thing. Okay, so that might be the problem. Was that my light vector was opposite? So this is my diffuse thing. Looks generally right. So now let me look at the other ones again. Yeah, yes, that's what I want. Okay. I just had my light vector flipped. So that's my normal distribution function. So it's definitely at least something that I want. And then here's the geometry term. It's really interesting to see where it's dark and light. It like darkens things on grazing angles, it looks like. So now let me combine G NDF times G. So here we go. That's like molten metal blue ocean. Also, a big part of the look right now is my tone mapping that I hacked together at the end of last stream, which I don't like that much because it's desaturating too fast. So like you see those gray patches, which I don't think it should be gray at that. Yeah, it is weird. Desaturation in the midtones. So I'll have to figure that out later. That's just because I like hacked together a tone map function last week. Okay. In any case, I'm confident that I have NDF and G working. So now let me just add in the F. The Fresnel term makes it a lot dimmer. Maybe I can increase my albedo. Or the brightness of the light, maybe. Yeah, I'd say that looks pretty good for like a. I mean, it's not the final BRDF at all. So let's just plug in the actual. Specular value. So here we go, and then let's multiply it by some value. So here's our specular. That grid is pretty harsh. I really got to figure out the tessellation stuff. The underside of it looks pretty cool. I feel like I might not be clamping something that I'm supposed to for it to look like that on the bottom. Well, I'll figure out those issues later. So my thought is I don't think I need a diffuse term for now. What I do need is a basically, okay, I do need a diffuse term, but I'm not going to use Lambertian. I'm just going to use like a flat color diffuse using the energy conservation thing. So yeah, now that we have specular, I didn't get this far when I was reading earlier. I'll definitely look into those, yeah. Because yeah, the distance speckling is pretty nasty. Okay. Where do they have their diffuse term? Diffuse term times albedo times radiance times n dot L. Okay, so they have specular times radiance times n dot L. So that's something important. I need to be multiplying specular by n dot L. Okay. And so they're calculating the amount of the albedo based on this. I think this is the energy conserving term. Which paper was that? The ocean water one. No, that's not it. Oh, the GGX thing. Got it. Yeah. That's a pretty based combo. So here they just have multiply by 1 minus metallic. If metallic is 0, it does nothing. We're not metallic, so 1 minus specular. Yeah, they literally just have 1 minus specular times albedo over pi. Well, I don't need a diffuse term. What I do need is I guess maybe it's emissive is what I'm thinking of to approximate the like scattering of the ocean. I was reading I know Tessendorf talks about the optics of it. I don't know how he approximates. If we can get it looking like this, then it will be in good shape. It does not quite look the same. Caustics. I'm not going to try to do caustics right now. So yeah, they actually do have a Lambertian term here, I think. So maybe I should have just like a flat emissive ocean color. And then also a Lambertian term, maybe. I think I'm going to turn off my tone mapping for now just so I can tell what's going on better. Oh yeah, it already looks like that. Tone mapping's not doing anything right now. Where did my Tessendorf go? Yeah. Okay, let me change the sun to be back to a different angle. That looks pretty nice. Okay. Almost there. Let me try just adding a flat emissive to it. Much smaller than that. It's probably not very good to do it this way. Anyway, it doesn't look very good. Like, it doesn't look like an ocean in any case. I'm gonna see if this paper has any good shading stuff. This one's pretty short, doesn't have a lot of detail. Reflection. Okay, this is pretty simple. So there's sky reflection, sunlight, and local reflection. Refraction is decided by the scattering object color inside the water. Oh, this is for, I'm going to do this eventually, like when I have, that's a good point, yeah, water is probably a lot smoother, so maybe roughness should be 0, or like something very low. Sky texture, yeah, that's a good point. I should do just like a flat blue sky color for now, and then make the specular reflect that. Yeah, like clouds and stuff would be a lot prettier. I do not expect to make clouds or like, especially not an actual like sky cube map this stream, but I eventually do want to do that. Kind of want to see, oh yeah, I should try making it in this direction. I want to see if I can get some like Fresnel streaks. That looks pretty nice, apart from just like the horrible aliasing. Gradient, yeah. Okay, I can do that. So let me decide on some sky colors. Let me open a color picker. Okay, let me also link up Google Images, sky. Okay, so we've got 81, 127, 165. Although that's sRGB, not linear. I hope the shader compiler's const propagation just gets rid of all this crap. I have minimized everything. Okay. So yeah, with the specular you have, this is just like a white color, and then I think I want to just dot it or multiply it with the sky color. So what did I do wrong? Okay, so that's like vaguely sky colored. But yeah, let's make it a gradient. So we need to like somehow, let me just do like, what color is being reflected? Like what is the actual reflection vector here? So it's like it's the ambient term. No, it's not. Specular. How do you use like a cube map for specular? I think it would be different from, yeah, it's not the color of the actual, this shouldn't be sky colored, this should be sun colored. And then what I need to do is take perfect mirror reflection, which is just going to be reflecting V around N, and that gives me my sky vector. GLSL has like a reflect, right? Yeah. Yeah, let me just call the reflect function I is V, N is N. And then we calculate sky by yeah, exactly. Okay, blur with perfect reflection. So now I'm going to have a sky thing that lerps from the top to the bottom with this to like a darker version of it. Maybe this is the darker one. I need to do this at the top. I mean, this is a weird photo with like a bunch of color grading and stuff, so maybe this can be my top value. $114, $191, $229. And then we have basically the reflected vector that has a z that's going from 1 to -1. So that should give us a... And then I also want to actually render that sky map so I can see that it looks good, but... Okay, so let's just add sky to it. So. Oh, I added this on the commented out part. I'm so dumb. So I don't think I need to like do a energy conserving thing here. Because it's a different direction through the BRDF. I really need to like figure out how this works better. Okay, I still don't think this looks anything like the ocean. The waves are also nothing like an ocean, but like I feel like I can get the surface looking a lot more like an ocean than it does. Let me tilt the sun further down. The reflections look good at least. I mean, the specular does. I'm gonna just look up photos of the ocean. Yeah, like I'm using a very low frequency sky map right now, so like I don't think I need to really blur it based on roughness. Do I need to? Yeah, that's a good point. Maybe I should switch gears to work on the waves. Like in some ways it looks pretty good. Yeah, that's what I was thinking. The Fresnel is like not quite what I want. Let me just make it flat. Like that looks like Fresnel is supposed to look to me, I think. Yeah, you're right. That's what I was thinking. Fresnel on the sky map. So let me and the Fresnel term applies. It's kind of independent of these. So Fresnel term you compute once, I think. Why do they have it in the for loop for the lights then? Oh, because H does depend on the light. So yeah, we do need to recalculate Fresnel for the sky. Fresnel term is going to be so Fresnel-Schlick takes the. You look again at what. Where theta is the angle between the two normals. Incident light and the normal of the surface. So yeah, in the case of the specular reflections, the theta is the angle between view vector and half vector. In the case of the sky map reflections, it's going to be theta is n dot reflected, I believe. So theta here is dot reflected, and I think that's right. So that gives me Fresnel on the skybox reflections, which would look better if I were actually rendering the skybox, I think. What am I doing wrong? Oh, I'm not changing the height of the hole. I'm being dumb. There we go. That's what I wanted to try. So I think my Fresnel is working correctly. Let me try making the sky reflection vector be gradient across the sky instead of okay, so that's not a very good dark color. Let me swap these. So gross. Oh, there we go. I had my skybox gradient across this way rather than vertically. Somehow that vertical variation in the skybox just like really makes it look so much more like the ocean. Okay, let me make this be taller again. It's got a ways to go, but I actually think this is getting somewhere. Okay, I honestly think it'll start looking a lot like the ocean once I make the waves look like an actual ocean. Let's maybe make the sun be much brighter. Okay, so it's not quite where I want it to be, but it's kind of getting there. I think probably adjusting the relative colors and brightnesses of things might also be pretty important. But for now, I'm going to move on to making my actual ocean model be Gerstner waves. So going back to good old friend Tessendorf, let me go down to Gerstner waves. So it's basically a Fourier series, I think. If a point on the undisturbed surface is labeled xz and the undisturbed height is y equals 0, as a single wave with amplitude a passes by, the point on the surface is displaced at time t to k is the wave vector, which points in the direction of travel of the wave, and magnitude k, so normalized k times amplitude a times sine of k times x minus omega t So basically Gerstner waves are a single sine wave in one direction. And then you sum together a bunch of them going in different directions. A set of wave vectors, a set of amplitudes, frequencies, and phases. And I'm sure that choosing the right set of wave vectors is like super important. How do you get a height field out of Gerstner waves? Because this is talking about these points move back and forth. Trying to do something about aliasing. Basically trying to use distance from the camera as how much to smooth the normals by, just as like ad hoc. There's no analytics. That's sad. Okay. So basically just... Do I still have the GPU gems open? They just use a texture in this one. I'm going to try to repair this garbage that I was using to fix the aliasing. That's kind of smoothing it too much. It's doing what I wanted it to, but like, just kind of ugly. So I might just take it out. Okay, giving up on that for now. I will figure this out later. Okay, back to our ocean. Some nice aliasing. Sum of signs. Okay, yeah. Gerstner wave function. Yeah, has lateral movement. Actually, you know what? I could just do lateral motion. There's no problem with that. As long as it's not too big. Because I'm doing this with vertices, so it doesn't actually have to be a height map. And I think that my normals will even still work. As long as because I'm just taking finite differences across a function, a parametric surface. Yeah, I'm pretty sure it'll still work even if I use lateral displacement. So I can just use Gerstner waves as is. It doesn't have to be a strict height function. So let me replace these sine waves with Gerstner waves. And what they look like. Where did it go? Gerstner waves. So x equals, so now I need to change my f from being a scalar function to a vector function. I'm glad this just pretty simply lets me do that. It solves the problem pretty well. Nice. Okay, let me fix my offset coordinates because, okay, W and S should be modifying Z, not Y. And then A and D are X, and then R and F are Y. So now we can just say vertex position is F of X comma Z There we go. Something's weird with my normals though, I think. Okay, so position, I plug in my original position plus offset. Okay, yeah, it's probably the normals that I'm messing up. So nor takes X and Z, and you plug those into F, take finite differences. It's hard to tell what I'm messing up here. Oh yeah, I should normalize these. Still has that same problem. I don't know what those spots are. Yeah, it's like my normals are not matching up with my actual surface. It's like they're a texture painted on that doesn't match it. X cross Z gives you Y, so that makes sense. Hmm. Okay, let me look at what I had here previously to see what I messed up. So what I was doing was y equals f x comma z. Okay, position equals my original x, y, and z, and then adding it to y. Still having that normals problem. I'm feeding offset into both f and normal. Oh, I'm feeding different. Yeah, typo. That's all it was. There we go. Back to how it was. So now I can actually use Gerstner waves. It's like ignoring the offset. So position. Oh yeah, I need to not feed offset into the x and y. That's the problem. There we go. Thanks. Yeah, I think it's looking pretty good. The flat emission for the volume scattering thing is like, doesn't look horrible, I think. Oh wait, I don't even have that on. Let me see. Okay, I don't think it looks very good. Okay, now I can actually do Gerstner waves. I know I've said that like 10 times now. A single wave, let me just write a little function for this. So a wave with coordinate x and z, we're going to return Um, so we have a sum of sine waves where you feed just basically xz dotted with the wave vector, I think. So we have, let's say our t value is dotting the position with the direction, and then we plug that into sine and cos for our x offset and y offset. What is k again? Oh yeah, okay, k is the wave vector. So normalize the direction times amplitude times sine of t wait, t is already our uniform for the time. We have a frequency times t, and then we have So let's see how this works. Probably wrong. Very confusing. So this is hanging me for some reason. Just getting like massive overdraw or something. So closing the tab till I can fix that. There we go. Okay, so that's something. We have a single wave, which is what this looks like. Let's turn up the frequency a bit. Yeah, that makes sense. That happens whenever I like really overload the GPU. Okay, let me try superimposing a few of these. They're inverted? Okay, yeah, you're right, definitely. Okay. Let's turn down the frequencies a bit, I guess. This looks a little bit silly. So I'm just choosing random ones. So it's not like statistically like the ocean, but I think it's just any of them at all looks way better than pure sine waves. Yeah, I'm fairly happy so far. It still is like really missing a lot compared to the actual ocean. I'm not quite sure where to go next with that. I'm curious if maybe some basic model of like I get more transmitted ocean color depending on the view angle. Frequency from wave number. Yeah, I've just been bullshitting all of these. Okay, that looks worse than before. But yeah, I should actually do this in a principled way. And honestly, the distant aliasing is not as bad as it was. I should still get like a solid solution to it, but I think it's not so horrible now. Oh, you know what's happening? I think I'm messing up my tessellation frequency by moving the vertices themselves. That is not right. What am I doing wrong here? I had it right before. I mean, that looks cool. Just a bunch of noise. It's not correct. For what not to happen? Sorry. Oh, there we go. Okay. Yeah, I fixed my tessellation issue. So now it's still tessellated finely close to the camera. Okay, I think I made some good progress today. I'm kind of running out of steam, so I might hang it up pretty soon. Yeah, that wasn't actually the problem. The problem was an unrelated bug about how I was computing my vertex positions in the first place. Okay, one more thing. Actually, I don't know if I want to do this. I'm going to do a constant color sky. Just using the color from my sky right here. So in my GeoClear color, I'm going to use this instead. Okay, it looks a little bit silly when it's not the gradient. Okay, so I'm messing up the gamma somehow. So since I'm doing my own gamma conversion, and I don't have frame buffer sRGB on, my clear color should be sRGB. So that means I don't need to be doing any of this correction stuff. Okay, what was my other sky color? 81, 127, 165. Oh, I do need to be dividing them by 255 though. There we go. That's a decent sky. That's actually what I'm using anyway. Yeah, so like actually if it's an sRGB, if you turn on the frame buffer sRGB extension thing, it's linear, I think. But in this case it's sRGB. Okay, so this doesn't really look like an ocean. I have a long way to go before it looks good, I think. but I made some good progress. I implemented GGX, the Cook Torrents thing, and I implemented Gerstner waves, although I didn't do like a principled statistical stack of them, but yeah, I'm gonna hang it up for today. Okay, so gonna go get Hubble.
Buddy, you wanna come say hi? Come here. Come here, bud. Want some treats? Okay, come on out, buddy. Come here. Come here, bud. Come here. Come on. You sleepyhead.
Okay, here we go. Sleepyhead puppy. Okay, so I have a long way to go to have an actual good-looking ocean. But I think I made good progress for... I've spent on stream like 6.5 hours and a little bit of time off stream fixing stuff. But yeah, it's still like 350 lines. The majority of it is shaders at this point. Anyway, I think it's pretty good progress. Alright, thanks for tuning in, everybody. I will see you guys next week.